Image models can paint anything you describe. Language models can write code, lawsuits, screenplays. Robots are still the embarrassing cousin at the family reunion. Train a robot to fold a shirt. It folds shirts. Move that robot one room over, different lighting, different table, new arm, it breaks. But a small lab in San Francisco just published a robot brain that breaks the pattern, and the trick is almost insultingly simple. Here is why robots have been stuck. Language models eat the entire internet. Trillions of words, every style, every domain, with all the noise and contradictions baked in. Robots eat curated demonstrations. A human grabs a teleoperation rig, performs a task, saves the recording. Repeat 10,000 times. It is slow, it is expensive, and almost everything in the dataset is clean and successful. And here is what that cost you. Language models compose. Ask one to write a haiku in JSON about the French Revolution, and it just does it, even though no haiku in JSON about the French Revolution exists in its training data. Robots do not compose. A robot trained on shirts and trained on cups cannot fold a shirt into a cup, or wrap a shirt around a cup, or put a cup on a shirt. Every new task is a from-scratch data collection effort. That is the wall. The obvious fix is to throw more data at it. Pool every robot recording you have. Mix in autonomous rollouts. Mix in failures. Train one big model. Done. This does not work. Every recording in that pool was made under a different strategy. A fast expert. A slow beginner. An autonomous run that succeeded. An autonomous run that failed halfway through. When the model averages over all of them, it learns the average. Slower than the expert. Worse than the autonomous rollout. Sometimes literally a step away from the failure. Curating just the clean demonstrations is what everyone does. But that throws away most of the signal, including the failures, which are exactly the data you need to learn what not to do. Here's what physical intelligence did. Take every trajectory in your dataset, the good and the bad, then label each one with what kind of trajectory it was. Each example gets 3 kinds of context on top of the camera observation. A subtask description, like open the fridge door, a set of future state images showing what the world should look like after the subtask succeeds. A metadata block with 3 fields, speed, quality from 1 to 5, and whether a mistake happened. And a separate tag for the control mode, joint angles, or end effector pose. Now the model is not averaging anymore. It can see that the fast trajectory was quality 5. The slow one was quality 2 with a mistake. It learns both, and it learns which is which. Failures stop being garbage. They become labeled examples of how to fail, which is information. Suboptimal autonomous rollouts become signal. Even videos of humans doing tasks with no robot at all get folded in. The data problem flips. The model itself is roughly 5 billion parameters in 2 pieces. The first is the Vision Language Backbone Gemma 3, a 4 billion parameter vision language model that already includes a 400 million parameter vision encoder inside that count. The second piece is the Action Expert, 860 million parameters. Its job is to take the language backbone's output and produce a chunk of 50 future robot actions all at once. It produces those actions through flow matching. Same idea as image diffusion. Start from noise, iteratively denoise toward the right answer. Except instead of pixels, the answer is 50 time steps of joint angles. There is one subtle but important detail. Gradients from the Action Expert do not flow back into the language backbone. The language model is supervised separately on a discrete tokenized version of the actions, so its representations stay clean and stable. The Action Expert hooks into them but cannot corrupt them. The recipe is called knowledge insulation, and the Pi 0.7 model uses it directly. Then there's the world model, a separate 14 billion parameter image generator, fine-tuned to imagine future states. Give it the current camera view and a subtask, and it generates what the environment should look like after the subtask succeeds. The robot then aims for that image, and the whole thing runs in real time. The Action Expert generates a 50-step chunk in roughly 40 milliseconds in its lean configuration, or about 125 milliseconds with the full memory and image goal context turned on. A technique called real-time action. Chunking absorbs that latency, keeping a 50 Hz robot running smoothly. The world model is much slower, generating each new imagined image in just over a second, so it runs in a separate thread, refreshing the goal only when the subtask changes. The robot keeps acting on the latest goal image available. Here is where the captioning trick from earlier pays off. Because every trajectory was labeled at training time, the metadata is now a control surface at inference time. Want fast, expert behavior. Set quality to 5, mistake to false, and tell it to be as fast as the fastest 15% of training runs on that task. The model produces a fast, clean trajectory. Lower the dials and the same model produces something slower and clumsier. Same weights, different mode. Then they apply classifier-free guidance, the same trick image diffusion models use to make outputs match the prompt more strongly. They run the model twice. Once with the metadata, once without. They subtract, scale up the difference, and push the policy further toward expert mode. And here's the punchline chart. As you add more low-quality data to training, models without metadata get worse. The PI 0.7 model, with metadata, just keeps improving. Lower quality data becomes free fuel. When you train this thing on a giant pile of mixed quality data, with rich captions on every trajectory, surprising things start happening. Start with the headline result. On dexterous tasks like making espresso, building a cardboard box, and folding laundry, the single generalist model matches or beats the specialist models that physical intelligence had previously trained with reinforcement learning, one specialist per task. One model now does the work of many. 3 other behaviors are worth singling out because each one points at something deeper than benchmark scores. First, cross-embodiment. The model was trained mostly on lightweight bimanual arms. They tested it on a heavier industrial arm it had never seen. On a shirt folding task it had no recordings of on that arm. When paired with sub-goal images from the world model, it folded the shirt at roughly the level of expert human teleoperators. And it did not copy the human strategy. The human teleoperators tilted the shirt and used a particular grasp. The model figured out a different grasp better suited to the new arm's geometry. It generalized the goal, not the motion. Second, verbal coaching. Walk the robot through a 5-step task it has never seen, in plain language. Steps like grasp the handle, open the air fryer, drop in the sweet potato, close the air fryer. The model follows along live. Then take those coaching transcripts, fine-tune the same model to produce those instructions on its own, and the robot does the task autonomously, with 0 new demonstration data. Third, breaking dataset bias. In the training data, trash always goes in the bin and dishes always go in the bussing bin. Tell the model to do the opposite. Put the trash in the bussing bin, the dishes in the bin. Older models barely manage. They mostly copy the training bias. This one obeys the instruction. The bottleneck in robot learning has always been treated as a data shortage. Collect more demonstrations, the thinking goes, and the rest takes care of itself. This paper argues something different. The bottleneck was never the amount of data. It was that the data was unlabeled at the strategy level. The model could not tell a 5-star expert episode from a 2-star failure, so it averaged them. Caption every trajectory and the failures, the autonomous rollouts, even the human videos all become usable signal. There is still a long road ahead. A single model that can fold any shirt on any arm in any kitchen does not exist yet. But the question has shifted. Not how do we collect more demonstrations, but what should we be writing down about the demonstrations we already have?